Hello, it's Keith here, and this is lesson 2 of the SuperH assembly programming tutorials. Now, last time we got started with SuperH and we looked at the basics. Now, this time we're going to continue with that. We're going to look at some slightly less basics. We're going to do a bit of recap on last time. What we're going to do is we're going to look at the addressing modes, the various ways in which we can get and store data for our calculations. So we're going to go through them all one by one. Some of them are very simple and you've seen before. Some of them are a bit more complex, and some are things you really probably won't need to know at all, things that you may never actually need. But I think it's worth looking at them all in this very rigid way, going through each one stage by stage, because I think it makes everything very clear and you have a good foundation of understanding that you know all of the possible addressing modes and how they actually work. It's very handy when you're reading documentation as well, because some of these, the terminology that I'm using, things like this here, these you will actually see in the official documentation, and some of them, when I saw them originally, were a little bit vague. I didn't quite understand what they meant, or things that it was referring to as addressing modes. I didn't understand where they actually applied. So we will see them all one by one today. Let's go over and let's take a look. Okay, so it's lesson 2. So we're looking at lesson 2.asm today. And just for a bit of fun, we're going to use the 32x this time. We used the Saturn last time. We're going to use this 32x now. Fun fact about 32x: 32x was a Genesis extension, and the important thing about that is there's actually 2 cartridge ROMs in 2 different assembly languages. The one we're going to be looking at is the SuperH part, which we're assembling with ASW, but there is an option here to assemble the 68,000th bootstrap, if you will, which is also needed for the 32x, and that's done with VASM. So if you select that option here, today's example will not assemble because that's the wrong one. You need to select the SuperH part here for the example to run, and if we just run that here, you will see it does indeed run fine, so we will have a good day. Now, how does today's example actually work? Well, just as before, we've got a jump block here, and what we need to do is we need to unrem one of the options here to jump to the section of the code with the samples that we're going to try out today. Now, what we're going to do is we're going to go through each of the addressing modes as they were described in the official documentation, and we're going to try them out with a few examples. That's how I like to do things. So the first one we're going to look at is known as immediate addressing. So what this is this is simply a value that is stored within the command itself. Now, as I've said before, all of the commands assemble to a 2-byte command, 16 bits. And so because of this very small size, some 32-bit processors have 32-bit commands. The SuperH only has 16 bits. So the range of the immediates is more limited, and so the legitimate immediate value is -128 to +127 with the vast majority of these commands. So you can see here we're loading a value of -100 here into R0. As before, the source is on the left. In this case, the hash marks it as an immediate value, and the destination is on the right of the comma, R0, and then we're loading the value 1 into R1. We're loading the value 100 into R2. As I say, any value from -128 to +127 is perfectly legitimate. And then we're showing these values on the screen. So this monitor3 function is showing the values on screen as before. So R0 has the value 9C. Well, what does that mean? Well, it means I can't find my calculator. So if we load up our calculator and we put in a value of 100 here, you can see the 100 in decimal is 64 in hexadecimal, which you can see over here in R2. So that looks like that's probably right. -100 is lots of F's and 9C. Well, we can see something like that in R0. So that looks like that is right. And of course, the value 1 is in hexadecimal just 1. So there we go. So those values have been loaded correctly. Now, those are signed immediates. So an 8-bit immediate, when it's signed, has a value of -128 to +127. But there is a case where the immediates are actually unsigned, and these are known as 0 extended. Now, what is the case that this happens? Well, this is the logical operations. Now, logical operations we're going to cover in a later lesson, but these are things like AND or XOR. They're very common commands you see on every assembly language, and I say we'll cover them later. But these basically, it doesn't necessarily make sense for them to be sign extended. You could argue that it is worth doing, but in the case of the SuperH, they are 0 extended, which means that basically the byte value we specify becomes the low byte that is used, and the remaining bytes are all zeros. So what can we do with this? Well, basically, what we're doing here is we're using an AND with the destination as R0, and we're ANDing this value with R0 and storing the result in R0. Now, when we do that, the value 9C with all those Fs becomes entirely zeros and 9-0. Now, why 9-0? Well, the top nibble was retained by these bits here, so that kept the 9. The bottom bits here lost the C, so that became a 0. And as I say, it was 0 extended, so all of the extra bits became 0. If it was sign extended, those bits would have all been retained, so we can see it is indeed 0 extended. Now, just a fun fact here, but the AND command on the SuperH, when it's working with an immediate value, this only works with the register R0. If we try and actually assemble this command with R1 as the destination, we will get an error. If I just extend this up here, it says addressing mode not allowed here, and what it's referring to on line 48 is the fact that R1 is not a valid destination for an immediate value there. So that's what that means. So that's immediate addressing with an 8-bit immediate. That is arguably the simplest addressing mode, but maybe there is a more simple one. It depends how you define simple. But rather than an immediate source and a register destination, we can actually use a register source with a register destination, and this is known as direct register addressing. So the syntax here is R for register and a number. So here we are using R0 as the source and R1 as the destination, and we are moving the value from R0 into R1, although the term move might be a little bit misleading because it's more of a copy, because the value in R0 stays the same. So at the start of this section, R0 contained the value 90, R1 contained the value 1, and R2 contained the value 64. But after we did our first move from R0 to R1, you can see that R0 contained the same value and R1 has that value as well now. And then after that, we moved the value from R2 into R0, and you can see that R0 went from 90 to 64 because that's the value in R2. So as I say, a very simple addressing mode, just transferring values between registers. And this is, of course, immediate values. As I said before last time, if you need to work with values outside of the range of -128 to +127, the assembler will do that for you. If you specify the value in this same format, it will just store the actual data at this literal org defined by LT_org. It automatically puts them at that position. However, those arguably aren't immediate values because they're actually, although they look the same in the assembly, they're actually being stored as a memory offset from the current program counter, and we'll see that later on. So while it may look the same and from a programmer's point of view function the same, they aren't actually the same thing. Okay, so now let's try these indirect addressing modes. Okay, so what we're going to look at now is known as indirect register addressing, and this is defined by an @ symbol, an R, and then a register number. Now, we did look at this briefly last time, and what this means is the source or destination of our command will be at the address in a register. And so what we're going to do here is we're going to load the value test address here, and test address, you can see we've defined a block of test data down here. And what we're going to do is we're actually going to use this data as our source. And so we're loading the test address into R5 here, and we're loading the test address +4 into R4. So we will effectively be pointing to this second value here in R4. And then R3 we're loading with this test value here, FFEEDDCC. And we're going to use the addresses in these registers via indirect register addressing as sources and in some cases destinations for our commands. So let's see what we actually do here. So what we're going to do is we're going to work with different lengths of value, and we're going to load some test values in. So first of all, we're going to load a long value. A long means 32 bits on the SuperH. It varies depending on the assembler and the processor, but in this case it's 32 bits. So we're going to load 32 bits from the address in R5 at R5, and the destination is going to be R0. Now you can see here that our test data is 1, 2, 3, 4, 5, 6, 7, 8 here at this address here, and that is the address that we loaded into R5. And so when we load our first test value, our 32-bit long value, R0 becomes 1, 2, 3, 4, 5, 6, 7, 8. That's as a result of that first command here. Now the second command is going to load a word. That means 16 bits on this processor. So we're loading a 16-bit value into R1. Now the processor is configured in big endian mode. What that means is that when we load a 32-bit value, the most significant byte is the first one in memory. The SuperH can be configured to be little endian, but in this case, with these systems we're looking at, it's configured as a big endian processor. The point being that when we load our word, we get a 16-bit value of 1234, as you can see here, and it's been extended to fill the register there. Now, the final command we're doing is we're moving a byte from the address in R5 at R5 into R2, and so we simply get the value 12 because that was the first byte at that address. And in all of these cases, R5 has been left unchanged. So there we go. Okay, so what we've done here is we've just dumped the memory to the screen, and you can see we've got that 1, 2, 3, 4, 5, 6, 7, 8 value, and then a series of F values. Now, those F values are being pointed to by R4. Now, what we're going to do next is we're going to move the value in register R3 to R4 here. And because we're not specifying a length, you can take it as read that that is moving a long. Now we're moving the value R3 here to the address in R4. R3 contains the value FFEEDDCC. Now previously, that address being pointed to by R4 contained entirely Fs, but after that command transferring the value in R3 here, you can see that that value in R3 has been transferred into memory there, so that memory has been changed. So that is how we can read a value from an address in a register, and that is how we can write a value to an address in a register. In both cases it's the same, it's just an @ symbol, and the register as in both cases the source parameter is on the left, whether that is the address in a register or a register itself, and the destination is on the right, whether that's a fixed register or the address in a register. So that's how we can use indirect register addressing, and that's the simplest of the ways of reading or writing data to and from memory. There are other more advanced ways which we are going to take a look at just in a moment. Okay, so that is something that's definitely going to be something we're going to need. The one we're looking at next is actually quite interesting because it's actually more important than it might immediately seem. I mean, it's going to seem pretty important anyway, but it has a second function. Okay, this is known as post-increment indirect register addressing. Well, what does this mean? Well, in the same way as before, we're going to use the address in one of our registers, so the @ symbol defining indirection, but this time you can see there's a plus after the register number and name. So this will appear like this, so R5, at R5 plus, at R5 plus, and what this actually does is it actually changes the value in R5 with each of our commands. Okay, well let's take a look. So once again, we've got some test data, basically the same, we've just redefined it down here. There are distance limitations with some of these commands, so we're repeatedly defining the same data for each of these tests. So we've defined we're showing it to the screen here, and then what we're doing here is we're moving that test address into R5, so R5 points to that test data. Now we're going to do a series of moves. So the first time here, we're moving from the address in R5 at R5 and then plus, and we're moving that into R0. Now what this does is it moves effectively a long, because we didn't specify, but it defaults to long, and long is 32 bits, 4 bytes. And so what this does is it moves from the current address in R5 into R0, and then it adds 4, that's the number of bytes we read in, to R5, changing the value of R5 after the read was done. So the read is done from the address in R5, and then R5 is changed. And that is referred to as a post increment because the R5 goes up increments after the read. So that's moving a 32-bit value into R0. Move L is moving a 32-bit value into R1. Move W is moving a 16-bit value in R2 to R2, and then 2 will be added to R5 by that command because we've only loaded 16 bits. And then 1 byte is being loaded into R3, and 1 will be added to R5 by that command there. So this is our test data here. And you can see it contains 1, 2, 3, 4, 5, 6, 7, 8, a series of Fs, and then 1, 1, 2, 1, 2, 1, 3, 1, 4. And then after we read in R0 and R1 with 32-bit values, you can see R0 contains 1, 2, 3, 4, 5, 6, 7, 8. That's the first 4 bytes there. R1 contains all those Fs. That's the second 4 bytes there. And then we've loaded our 16-bit value into R2, and our 16-bit value has become 1112. Those are the bytes here. and then our byte has been loaded into R3, and R3 has been loaded with the value, where is it? 13 there, and that's that value there. And then R5, after all of these commands, contains the value 1CB here, and that will be basically pointing to the next byte in that position there, that 14 there. That would be the next byte read in. And so in all of these cases, we've been able to read in data of various lengths from our source register and automatically change the reading position. And this is a very, very useful command for all kinds of things when you're writing little games and things, or when you're even drawing a font to the screen, for example, which I'm doing here, where you need to read in those bytes of your font and then process them and get them to the screen. And you want to consecutively read those bytes of the font. In games, you'll want to read in consecutive bytes of your tile map or your game scripts and things like that. So this is a very, very common thing you'll have to do. And if you didn't have this or post increment, you would actually have to have a second command doing the increments, which is likely to be slower. Of course, it depends on your processor, but generally it will be. So that is post increment, very, very useful, and you will use that a lot. However, there is another option, and that is known as pre-decrement. Now, post-increment updated the register after the read. Pre-decrement updates before rather than the register going up in value, it goes down in values. Now, this is a command we can use to store values to an address in a register, and we're actually updating the register before we perform the store. Now, you might initially think, well, why on earth would you want to do this? Well, actually, this is something that you will need quite a lot, and we'll see why in just a moment. So what we're doing here is we're storing the 32-bit value in R0 into the address in R5, but first we are subtracting the amount to be transferred from R5, so we're effectively subtracting 4 from R5 here. The next command, we're effectively also subtracting 4. Then we're doing a 16-bit value, so that will subtract 2 from R5, and then we are doing a 1-byte value, again, effectively subtracting 1 from R5 here. So let's see what happens when we've done these commands. We've loaded some new test values into R0 to R3 here so that we can actually see what's happened in memory. We've set R5 to point to the end of our test range that's being shown to the screen here before we start doing our stores. So the first value we stored was a 32-bit value of 1, and so what will have happened is the value in R5 will have jumped back to this position here between that FE and that 0 there, and then our 32-bit value, our 4 bytes, will be stored. So you can see those bytes have been stored there, and so that's what's happened there as a result of that first write. Our next value was -2, which is the value FE here, and you can see that has been stored by the second value before the first one because we are doing that pre-decrement. Now the next value, the 16-bit value in R2 here, this value of 3 here, well, that has been stored before that again because of that pre-decrement. And then our final byte value, our FC here, has been stored here. And the remaining bytes here are as they were before. So those bytes have been unchanged. That FF and that 78 are there from the previous value. So that is how we can use pre-decrement. Now, pre-decrement in that format doesn't necessarily seem as useful as post increment, but as I say, it's essential really for a special purpose. Now, our processors have a limited number of registers. A processor like SuperH has quite a lot, but it's still relatively limited when you think of the megabytes of data we might have to actually work with. And so often we will need to temporarily store and restore values in the registers for a period of time while we're doing another job. A very common example of another job would be when we're executing a subroutine. That subroutine needs to do its own work, calculate its values, and then return to the calling subroutine. And the calling subroutine needs to know that its registers contain the same values for the same purpose as they did before it started calling that subroutine, and so we need a temporary store, and that is the stack. Now, the stack in the vast majority of processes is known as a last in, first out stack. Imagine you're in tray at work and your boss keeps giving you jobs to do because he's horrible, and you don't have time to do them all, and so he gives you the first job and you start doing it, but then he gives you a second job, and so you put the first job into your in tray and start working on the second job, but then he gives you a third job, so you put the second job on top of the first job in the in tray, you work on the third job, complete it, and then you go to your in tray and you take the top job off the stack, which is the second job. You then work on the second job, finish it, and then you take off the first job. That's why it's called last in, first out. The last job put into the top of the in tray is the first one you take out of the in tray. Why am I talking about in trays? Because I think that's the best way to describe how the stack works. The stack is a last in, first out stack, and it puts all of the data that it needs for later in and takes them out in the reverse order that it put them in. So what we're doing here is we're using the stack pointer, and we are using predecrement here to store data into the stack, moving that stack pointer down in memory and storing the data we want to keep for later. And then at the end, we're restoring that data with post increment addressing, and so that is restoring our data from the stack. Now, the stack pointer, just to remind you, is actually register R15. SP and R15 are the same thing, so I'm using SP for clarity, but you could use R15 in the same way. And in a lot of ways, you could actually use any register in this format. It's just for convention, the R15 is the best one to use in this way. You could define your own mini stacks using other registers if you wished, but it's not something that generally makes a lot of sense. So what are we going to do here? Well, what we're going to do is we're going to use the stack pointer to back up and restore a series of registers. So what we're going to do is we're going to show the registers R0, R1 and R2 to the screen here. That's what that line is doing. We're then moving R0 onto the stack. We're then moving R1 onto the stack and moving R2 onto the stack using predecrement, effectively subtracting the amount transferred from the stack pointer before storing the value from the register. So that is making more space on the stack and then storing the value. We're then going to give R0 and R1 and R2 new values here, and we're going to show those to the screen. Okay, so that is just confirming that we have changed those values and proving it by showing the new values to the screen. And then finally, we're going to pop the values off the stack and push and pop often terms, or push and pull, depending on your preference. But we're going to pop these values back off the stack. And it's important to notice that R2 is being popped off first, but it was pushed on third. And R0 is being popped off last, but it was pushed on first because, as I say, it's a last in, first out stack. So R2 was last in, so R2 is first out. Now, let's take a look at our values on the screen here. So at the start of our test here, R0 contained the value 1, R1 contained this value 6, loads of zeros, 1 CO, and R2 contained 1 0 here. Then after our test here, R0 contained 1, R2 contained 2, and R3 contained 3. But after we pop the original values back off the stack, well, they contained the values that they did originally. You can see they've all been restored correctly here. So that's how we can use the stack to back up and restore values for later when we want to do some work in between with the same registers. Now, in this case, I've restored the values into the same registers as I pushed them on. Now, that is often what you might want to do, but it's entirely optional. The stack is a very powerful thing that doesn't really have any limitations, and that can be a good thing or it can be a bad one. Now in this case, I've pushed them onto the stack in the order R0, R1, R2, but I've popped them off effectively in reverse order because it's a last in, first out stack, but I've taken the last value that's the first out and stored it in the opposite register. And so when I've restored these, we've gone from a 1, that value with the 1 CO there, and a 1 0, and they've actually ended up in the reversed registers because I've popped them off into the reverse registers. And that might be exactly what I want to do, in which case I'll be very happy. But you can also make a horrendous mess like this. You see, as part of my subroutines, I will often need to back up the return address that is stored in the procedure register PR. That is the address that the code needs to return back to, and so I will often store that onto the stack. However, if I push more onto the stack than I pop off, or I pop off more than onto the stack than I pushed on in my subroutine, I may consume or hide that return address, and that will cause the return command to actually go to the wrong address and crash my program. Now, what I tend to do is I tend to indent my use of the stack here. So I've pushed 3 values onto the stack in a clump here. I've popped them off here, and so I've indented this part of the code to remind myself, hey, you've not really cleaned up the stack here. You should have done probably. So fix it up. And so I do that type of indenting, but it's entirely optional, and I just find it helps me out. You can exploit this kind of thing on some processors. The returner command itself will actually pop the return address off the stack. And one trick you can do is you can use the return address to actually call a subroutine by pushing the address of the subroutine onto the stack and then using that return address. You can do all kinds of crazy things like that when you get more confident. But at this stage, that's, at this stage, you're just going to want to really just push as much onto the stack as you pop off and make sure you understand how the order should work to retain the values in the same way. As I say, last in, first out, basically. So there we go. So that's how we can use post increment and pre-decrement to store and restore values. Now, what we're going to do next is we're going to take a look at indirect indexed addressing. Now, what this does is, in the same way as before, we're using the @ symbol and a register, and that is going to use the address in the register as the source or destination of the parameter. But what we're going to do is we're actually going to use a fixed offset to that address, an immediate value. Now, why would we want to do this? Well, this is something that's very, very common, even on the humble Z80. There will be often times where you've got a piece of code that's designed to do a job, and it needs a pointer to a block of data, and within that data, there will be various things you want to work with. Let's say we've got a sprite. That sprite has an X coordinate, a Y coordinate, it has a sprite number, and it has a amount of health if it's a game character. Now, all of these can be stored at different offsets from the base sprite object. And then what you can do is you can have lots of sprite objects and just pass that sprite object base, the start of that sprite data, to our subroutine, and then those offsets can be used within the subroutine to get the coordinates, get the sprite number for drawing it, get the life to check it's still alive, things like that. And that is basically what this addressing mode does. Our register points to our object, and our immediate offset points to the pieces of data that we know are possessed within it. Okay, so that's what we're going to do here. Now, the format you will see looks like this. You have the @ symbol, you have an open brackets, you have a number, an immediate number, and then you have a comma, and then you have the register number that is, and this is basically saying store R5 to the address in R5 plus 12. And this one, the absolute simplest, is really not using the displacement at all. This is basically saying load R1 from the address in R5 plus 0. This is just really a placeholder to show that that is a legitimate form. The next version here, this is basically loading from R5 plus 4 and storing the value in R2. Now, it's important to notice this isn't like post increment or pre-decrement. We are not actually changing the value in R5. This is just a this is just as part of the address calculation that addition is being performed. So we're not actually changing the values at all. Anyway, let's take a look at what has happened. So we're using this test address here, and we are showing the values to the screen here. And so basically what we are going to do is we're going to load some of these values in. So first of all, we're loading from offset 0 into R1. Well, offset 0 contains the value 1, 1, 1, 2, 1, 3, 1, 4. And you can see that has been loaded into R1. We're then loading from offset 4 into R2 here. So what is offset 4? Well, you can see those are the first 4 bytes. The second 4 are 21, 22, 23, 24. So that value has been loaded into R2. But it's important to notice that the value in R5 does not change throughout this. R5 still points to the start of that range. So R5 completely unchanged by this. Now here we've used these immediate values and we've specified them as just fixed numbers, which is a very common thing to do. However, as I say, with that example of where we want to specify to reference an X coordinate and a Y coordinate in an object, these might be at specific positions within the data block, but they may change later, and we may want to give them a clear label like XPOS, like YPOS, like sprite life, things like that. We can use symbol definitions for that. What this line is, this isn't actually something that's assembled into our program code. This is something that tells the assembler that the word myFavVal, the text string myFavVal, is equivalent to the value 8. So this is saying myFavVal equals 8. And what the assembler does is whenever it sees later on in the code myFavVal, it will replace that with the value 8. This line in the code, when it's assembled, will look no different to as if this part here was actually just the immediate value 8. It's just for my convenience. I can see the word myFavVal, and if we change myFavVal to be 9 later on, if I have a change of mind, all of the references will just change accordingly. Now this value we're loading into R3, and so this value of 8 will basically point to 31, 32, 33, 34. Now we have loaded in a long again, and so that value has been loaded in 31, 32, 33, 34. Now the final version here, we're actually storing R5 to offset 12 here. And so you can see that the value R5 has been unchanged throughout all of this. And you can see that value has now been stored to this address just here. So that has worked fine. So this can be used for loading or storing data. Now, there are a few limitations, so some things that we can't do. On the SuperH, the offsets have to be positive. We can't use a negative offset. That won't work. Now, we can work with words and bytes. However, if we work with a word or a byte parameter, the destination must be R0. We can't use R2 or R3 here. We have assembled this here, and you can see here we've successfully loaded a value from R0. We're storing it into R1 here, transferring it, and then we are loading a byte value, an 8-bit value here into R0. And you can see that the offset 4 contained 2122, which has been loaded into R1 here. And then the offset 5, it's actually the second part of that, so the 22 there has been loaded into R0. So those, we are able to work with words and bytes with this, but we are more limited in our possible destinations. Being a 32-bit processor, the SuperH it has more flexibility when it comes to working with 32 bits. Anyway, that's how we can use a fixed index. The index is only 4 bits. The offset is multiplied by the number of bytes being read. So if we're working with a byte, then we are limited to a value of 15. If we were working with a word, we would be limited to a value of 30. But you see, if I try and load a byte here from offset 16, we're actually getting an error message saying that the range is overflowed. But if we use a value of 15 here, that will assemble just fine. In the same way, as I say, because it's actually the offset is, when it's stored in the command, is actually relative to the amount loaded. So we can load from offset 16 with a word. That will work just fine. But if we try to load from offset 32, that will not work. We've got the same error message, range overflow. But in the same way, we could actually work with an offset of 32 on a long, because as I say, it all depends on the amount that's being read, the total range that is allowable. Now, in those cases, we're using an immediate value for the displacement. There may be times where we want to be more flexible, and what we can actually do is, rather than using an immediate value, we can actually use a second register as the offset, and this is known as indirect indexed register addressing. Now, the offset has to be R0. R0 is a bit of a special register on the SuperH, and so if we want to do this, R0 has to contain our offset, and another register contains the base, if you will. So we're going to use R5 as our base once again, and we're going to set our offset first to R0. Now, what we're going to do here is we are basically going to load into R1 from R5 offset by R0 here. Now, R5 points to the start of the range still, and so when we load in 32 bits into R1, R1 will contain the value 11, 12, 11, 13, 14, because that's the first 32 bits at our destination. We're then going to add 4 to R0, and we are going to move a 16-bit value into R2. Well, R2 then takes on the value 2122, because 4 bytes on is this value here. We're then going to add another 4 here, and we're going to read in a byte into R3. So R3 contains the value 31. That's because we've added another 4 bytes, jumping over the end of the line here to the start here, and we've got that value 31. We're then going to add another 4 to R0, and we're going to store the value in R0 to the destination R5 plus R0. Again, R5 is unchanged. In this, I'm just describing the calculation that's performed to get the destination address. And you can see here that R0 has been stored. R0 contained the final value of 0000C here. And so that has been stored there. So that that's something that's useful to have. I think this, for me, this is far more the addressing mode that I would tend to use, just because of the way I've tended to work with things. But that's definitely a very nice addressing mode to have. And if you were working through data in a more random sense, where the offset would vary depending on the data you were reading. For example, if you had some kind of virtual machine that you were reading in a script for in your game or something, that's something you might need to do. Now, all of those are ones that you will use within your code quite a lot. What we're going to see now are ones that might seem a little bit more obscure. However, a lot of the reason that they seem more obscure is because the assembler is actually using them for us. Now, what we're going to look at next is a command that uses an immediate displacement along with the program counter. Well, what is the program counter? Well, it's the current running line of code. Let's take a look. Okay, so what we're going to do is we are going to load a 32-bit value into R1 from the current program counter plus 4. Now, the way that the SuperH works, the program counter actually doesn't point to the current running line of code. The SuperH, being a more advanced processor than some of the basic ones like the Z80, it actually is reading ahead. And so a few bytes ahead are actually being processed while the current command is still running, and that is why we often have to use delay slots. These no-ops after all of our branches to subroutines are because there are delay slots, and that's because the processor is always looking a couple of bytes ahead. Now, in this case, when we want to use the data use an offset to the program counter and load the data in, we need to bear in mind the actual address that the program counter is genuinely pointing to. Now, the program counter is actually pointing 2 bytes ahead at all times, so it's actually pointing to the start of this line when it's processing this line. And so when we specify an offset of 4 to the program counter, that is actually pointing to this line here. Now, what we're doing here is we are loading, effectively in a rather roundabout way, this value here into R1, and you can see that has actually happened here. That has been loaded in. Now, why would you want to do this, considering how hard it is to calculate the address in the program counter? Well, you won't want to, probably not anyway. You won't want to do this, but you will want the assembler to do this, because do you remember I said before you could specify things that look like immediates, but they would actually be stored in the LT org address? Well, guess how the assembler is doing that for us? It's actually calculating the destinations relative to the current running line of code and putting them in as offsets like this. So this command is being used all of the time by the assembler to actually do the job of storing those immediates that can't be stored as immediates. So I don't think you'll probably ever want to use this as an actual command yourself, but the assembler will be using it all the time on your behalf. So it's an extremely important command to have, just not necessarily a command you actually want to use. So there we go. So that's what that command does and why it's important. Now, in that case, we were using it to load a value, but it's also a great example of how we can use a command called move A. Now, what this is it effectively moves an address. Now, what does this mean? Well, in all of these cases, there is a calculation being performed. Now, when we say something like this, what we're effectively saying is load in from the address at program counter plus 4. But there might be a case where we actually want to calculate that destination address, that effective address, and then use it later on without repeatedly performing that calculation. Doing so may be faster, and it also allows us to actually have that value and then make decisions based on that value within our code. And this is especially handy if we're doing things like relocatable code, or in my case is all of these programs run on multiple systems. Sometimes I might need the program to work in a different way just depending on the address it's actually, the data that I'm trying to process is actually being stored. And so what we're doing here with this move A command is moving the address calculated here into R0, and then we're showing the results to the screen. Now in this case we are showing the results to the screen, and our program counter here contains the value 0600250. Now we've effectively moved the value here into R0, and the value here is 0600250. And that is actually effectively the address that the program counter contained when at the point that it ran this monitor command. As I say, the processor is always a couple of bytes ahead, and so I've effectively tricked it into loading the same address as this was executing into R0. Now, as I say, I'm not saying you would necessarily want to use this specific command, but as of before, where we were doing these commands using offsets and things, and these commands here where we're using immediate offsets, maybe you want to use that same offset over and over and over and over again. You might want to just store that into a register and then use that register indirectly without the offset. That might be preferable to you. So that's a command that's worth bearing in mind, but it's not one that you're going to really need in the early days, at least. So I think it's worth mentioning, though. Now we're going to discuss some more for completeness purposes now, rather than actually you need to know them. And this is really the reason I'm explaining these now, is because when I looked at the original documentation, these are mentioned in the original documentation, and they are mentioned as a displacement type relative to the program counter. And I couldn't work out which commands actually use them, and I was being a bit of a thickie, I guess, because actually these aren't addressing modes to be used by you as a source or a destination of a calculation or transfer command. They're actually used by other commands that you use every day, and again, you don't think about how they actually work. And so these are basically things like the branch commands. So displacement, 12-bit displacement, or PC relative addressing 12-bit, is actually used by our branch commands. It's, as I say, we never specify these as a number, we never specify the processing program counter, but when we do a command like branch to subroutine here, the assembler is actually calculating the offset to the subroutines. And so what I've done here, I've got BSR show B here, and show B is down here, so this is some distance away, and I've actually assembled this, and I've checked the source code, and this actually assembles to the equivalent of BSR 30. We've got a branch here. This is not a subroutine, this is just like a go to. This is like a go sub, but a branch here, and this is effectively calculated as branch 8. And these are using effectively 12-bit offsets to the program counter. Now, as I said before, BSR and BIA, I said in the last lesson, these are limited in the amount of distance that they can jump. JSR and JMP, they use a register as their destination, and they can go anywhere, but they're not as convenient. But these are limited in their distance, and the reason they're limited in their distance is because they're only using a 12-bit displacement to the current program counter. So they've got a good range, but they are limited. So that's where displacement 12 comes in. Displacement 8 is also a certain kind of branch. This is the conditional branches. We're going to look at conditions next time, but basically this command means branch if true. So what we're doing here is we're comparing the value 0 to R0, and we've loaded the value 1 into R0. So when we do branch if true to skip D, well, that condition isn't true, so the skip doesn't occur, and we show the D to the screen. However, if I just change my code here, and as I would say, all of these are downloadable, and you are encouraged, not just welcome, encouraged to try changing them and to see how these work and maybe find things that I've done wrong if I've made a mistake. But in this case, hopefully I haven't. And so we're loading the value 0 into R0, doing the comparison. And this time, R0 does contain 0. So branch if true occurs. We skip over this down to D here, and the D is never shown because we skipped over it. And so, as I say, this is another kind of branch, a conditional branch, and this actually uses an 8-bit offset, so more limited than our 12-bit offsets, but these conditional branches often won't jump very far. As I say, those are ones that you're definitely going to use, but you probably won't realize you'll use, which is why I couldn't figure out how those addressing modes were used when I saw them in the documentation. And so the GBR points here, and so we are loading from an offset of 8. So we will be looking at this value 31, 32, 33, 34 here, and that is being loaded into R0 there. We are then storing the value in R0 to offset 0 with the GBR here. And so that is being stored into the first 4 bytes here, 31, 32, 33, 34 has been stored to the base of the GBR position here. Now, originally the values were as they are shown here. So that value originally was 1, 1, 1, 2, 1, 3, 1, 4. It's been changed though by that right there. I guess really we should have shown that memory to the screen first. Let's change the code here. Let's put a second dump of the memory here. So that is the original values for the memory, and the first 4 bytes have been changed by this command here. Now there are again some limitations to what we can do with this GBR. The source or destination has to be the register R0. The R0 register is a special case. In that case we tried to use R1, and we got an error message, invalid symbol there. That wasn't allowed. So we have to use R0 as the destination or source of our commands there. So that's how we can use those. Now with these we've been using an immediate value as the offset to the GBR. In some cases we can use the R0 register as an offset. For example, this command here, we're using the AND command and we're ANDing a byte, the value 0f, with the GBR offset by R0. R0 we're setting to 4 here. If we run this we will see that this has happened. So offset 4 has been ANDed with 0f here. That position used to contain the value 2, 1. After the AND, it contains the value 0, 1. AND is a bit mask. It basically says if the bit in the source and the bit in the destination is 1, the result is 1, otherwise it's 0. We're going to cover these in a later lesson, the logical operations like AND and OR. So if you don't understand that yet, don't worry. But it's a bit of a special case with the GBR, because we can do that with an immediate and an offset of R0, but we can't do a variety of other commands. Really, it's just logical operations that allow us to use R0 as an offset there. And as again, I think those kind of logical operations might be the kind of things you want to do with memory mapped hardware, and so that's why they've been provided to you. You know, you might want to clear a set of values at a destination within the GBR or something like that. So as I say, there are those kind of special commands, but it is more limited what they can do. Personally, I never needed to use the GBR when I was writing my test programs to do the monitor mem dumps and things. I never used the GBR. It was only when I came to actually sort of start digging into the instruction set and really try and understand how all the addressing modes were usable that I came to use that. So again, I'm really putting it there for completeness and so you understand it. I'm not saying you need to know it. If it looks too complex, just ignore it for now. I'm sure you'll understand it when you come to need it. Anyway, I hope you've enjoyed what you've seen today. Please like and subscribe because we've got loads more lessons coming. Thanks for watching and goodbye.